Hi students, today we are discussing some questions related with the force acting on the current carrying conductor placed in a magnetic field. Okay, now we can move to the questions. The first question is, given like this. A semicircular loop is given like this. Okay, and it carries a current I in the same direction. Throughout the loop, the current is in the same direction and the value of current is I, and is placed in a magnetic field B, and the magnetic field is acting perpendicular and inward, and its radius is given as what? R. What is the force on the conductor? What is the force on the loop? That is the question. Okay, here the answer is very simple. We already studied the net force acting on a current carrying loop of any shape placed in a uniform magnetic field is 0, provided the current should complete the loop in the same direction. Okay, so here when you are analyzing this loop, you can see the current is I and it is completing the loop in the same direction, like this, clockwise direction, and it is placed in a uniform magnetic field. So very simple, the answer is net force is equal to 0. Okay, so this is a very simple question, so remember this point. Okay, now we can move to the next question. The question is given like this. A current loop is given, but the current is flowing like this. From A, the current is starting and is moving in two directions like this. One is through this circular arc in this direction, in clockwise direction, and in the straight line segment or in the straight line section, current is in this direction. Okay, if you are considering this as a loop, we can see the current is not completing the loop in the same direction. From here to here, the current is in this direction. Okay, and from here to here, the current through the straight conductor is in this direction, not in the same direction throughout the loop. Okay, and this loop is placed in a uniform magnetic field. Since the current is not completing the loop in the same direction, we can say the net force is not 0. Okay. Now the question is, how can you solve this question? For that, I can explain some important points. First one is, you studied a straight conductor AB of length L and carrying a current I and is placed in a magnetic field B. It makes an angle theta. Then the force acting is given by vector F is equal to I into L cross B, and its magnitude is given as F is equal to ILB sin theta, where theta is the angle between the direction of current and the direction of magnetic field. So you can apply this equation for the force acting on a current carrying straight conductor placed in a magnetic field. If the conductor is not a straight conductor, then how can you solve? For example, you are given a conductor like this, a conductor of irregular shape AB, and carries a current like this I, and is placed in a magnetic field B. Then how can you solve this question? So there is a method. The method is this one. You draw a straight line from the ends of the conductor and take this straight line length as L effective length of the conductor. Okay, if the current is starting from A to B, you can mark the current through the effective length is what? I, like this, in this direction. So this is the angle theta. Then the force acting on this irregular shaped conductor placed in the magnetic field is given by the magnitude F is equal to I into L effective into B sine theta. So this is the equation for the irregular shaped conductor carrying current placed in a magnetic field. Okay, so here you can see there are two sections in this loop. One is a curved section of the conductor and the other one is the straight line segment. Okay, so the net force on the loop is the force on this segment also. The net force on this loop is the vector sum of the force on this section and this section. Okay, so here first you find out the force on this circular section. Okay, curved section. So the first point is, what is the force on the circular section? Okay, now here it is circular, it is semicircular section, and you can take that force as F1 vector, and the current is what? I. Since it is not a straight line segment, you have to consider the effective length. What is the effective length? This is the one end, this is the other end. The effective length is this one. So this is the diameter, that is 2r. Radius is r, so the diameter is 2r. So the L effective is 2r into B into sine theta. What is theta here? Since the current is starting from here to here, so in this L effective length, the current is starting from A to B. So the current is in this direction and magnetic field is perpendicular inward. So what is theta there? 90, sine 90 is 1. So this is I into 2r into B. So it is equal to 2IRB. Again, what is the direction of this force? You can apply Fleming's left hand rule. You take the left hand, then this is the direction of magnetic field. Forefinger is in the direction of magnetic field. Direction is perpendicular and inward. And what is the direction of current? At this point the direction is in this direction. So central finger is in the direction of current. Then the force will give the direction of the force. So force is in the upward direction. Okay. Next we want to find the force on this straight section. So force on the straight conductor. You can take that force as F2 vector. And what is the equation? ILB sine theta. So here the current is again I. What is the length? Length of this straight segment is this much. So that is again 2r. So 2r into B. What is sine theta? That is again what? 90 degree. So sine 90 is 1. So the answer is what? 2IRB. Again you have to find the direction by using Fleming's left hand rule. Magnetic field is perpendicular inward. Current is in this direction. So force is again upward direction. Okay. So what is the net force on the loop? So you can say net force on the loop is F is equal to vector sum. But here these two forces are in the same direction. So you just add. Then you will get F1 plus F2. So 2IRB plus 2IRB. The answer is what? 4IRB. So the net force is 4IR into B. So this is the answer. I think all of you got the idea. Okay. Now we can move to the next question. Question is, you are given a rod of mass m and radius r. Okay, and is placed on a two parallel rails. They are separated by a distance small l. And this rod carries a current in this direction. Okay, and it is starting from rest and it is rolling without slipping, that is pure rolling. Okay, and it is rolling, and you want to find what is the speed of the rod when it leaves this rail. That is the question. Okay, and the magnetic field is acting perpendicular to the rails and also perpendicular to this rod. And the length of the rail is given as capital L. Okay. So how can you solve this question? Since it is initially at rest, so to move the body in this direction, a force is needed. Okay, and we know that already a force is here, and that is called the weight, gravitational force, but it is in the downward direction. That is not responsible for the motion of this rod in this direction. So first you have to analyze what is the force acting in this direction. Okay, so there is a chance of a force in this direction because of this magnetic field. This is a current carrying conductor placed in the magnetic field, so there is a force. Okay, so you have to find the force both in magnitude and direction. If the direction is in this direction, you can say that force is responsible for its motion. Okay, so find out that force. We know the equation for the force acting on a current carrying conductor as F is equal to I into L cross B. Okay, so here the current is I. What about L vector? The length of the conductor is this one. So what is its direction? So you just consider this is positive x direction and this is negative y direction. Then if this is the rod I placed on the rail, then the length is this one. Okay, and the direction is taken in the direction of the current. So current is in this direction, that is positive z direction. So we can take the direction of L is in the direction of current, that is in positive z direction. So it is L k cap cross magnetic field along negative y direction. So it is minus B j cap. So the force is given as ILB into k cap cross j cap is minus I cap. Minus I cap into minus plus, so it is I cap. So it is clear there is a force of magnitude ILB is acting along positive x direction. So the force is in this direction. So this force is responsible for its motion in this direction. Okay, but here you want to find the speed of the rod when it leaves the rail after pure rolling. Okay, so how can you find it? We know that during the motion its speed goes on changing. So the kinetic energy of the rod changes. When kinetic energy changes, when there is a work. So according to work energy theorem, we know that work done by the net force is equal to change in kinetic energy. So to solve this question, we can use work energy theorem. So according to work energy theorem, we can write work done by the net force is equal to change in kinetic energy, that is equal to final kinetic energy minus initial kinetic energy. So what is the work done by the net force? So one of the force is mg, that is not doing any work, okay, because mg is in this direction, displacement is in this direction, so work done by the gravitational force is 0. And here the other force is this one, that force is in this direction and body is moving in the same direction, so the work done is positive because theta is equal to 0. So work done is given by F as cos theta. Here F into what is the displacement when it leaving the rail means it traveling this much distance, that is equal to L. So you can write the net work done is equal to the force is F and the displacement is what? L, is equal to final kinetic energy minus initial kinetic energy. What is initial kinetic energy? Initially the rod is at rest, so initial kinetic energy is 0. What is the final kinetic energy? We know that it is in rolling motion, pure rolling motion. So the final kinetic energy is the total kinetic energy due to translation motion and rotation motion, because rolling motion is a combination of translation and rotation. So we can say the final kinetic energy is equal to the kinetic energy of translation plus kinetic energy of rotation minus initial kinetic energy is 0. And what is the force acting here? ILB. We need only the magnitude, so ILB into L is equal to kinetic energy of translation means half mv square. So half into mass of the rod is given as m and v is the final velocity. So when it reaches here, we are considering its velocity or speed is what? V. So it is equal to half mv square plus rotational kinetic energy is given by half I omega square. So here again question, what is the value of I? I is the moment of inertia. Okay, so what is the moment of inertia here? So what is the moment of inertia here? If it is the rod and it is moving like this, it is rolling like this, so about this axis it is rotating. Okay, so about this axis you have to consider the moment of inertia, that is along the axis of the rod. So we know that in the case of a cylinder, we know that the moment of inertia about this axis is what? Half mr square. So you can substitute what? Half mr square here. So we get what? Moment of inertia in this case is what? Half mr square. And we know that angular velocity is given as in terms of linear velocity, that is equal to v by r. So you substitute, you will get what? I into L into BL is equal to half mv square plus half into I is what? Half mr square into omega square means v by r whole square. So v square by r cancelled. So the final is what? ILBL is equal to half mv square plus 1 by 2 into 1 by 2 is 1 by 4 mv square. So on adding that 2, we get ILB into L is equal to 3 by 4 mv square. And we need to find what is the final velocity, final speed. So we get v square is equal to 4 by 3 I into L into BL. So I LBL divided by N. So what is the final speed? So the final speed is given as V is equal to square root of 4 ILBL divided by 3n. So this is the answer. I think all of you understood this question. So the important ideas are explained. So remember these points. Okay.